Welcome back, and today I'm going to be looking at the amplitude locked loop. You may have heard of the phase locked loop, and that's been around since 1935, I think, invented by a Frenchman. The amplitude locked loop was invented by Archibald A.M.Pettigrew, or Archie Pettigrew as we knew him, who worked in Paisley. He's a very experienced engineer. He'd done about 20 years in senior positions in industry before he came to us in Paisley, the University of Paisley as it was then, which become the University of West of Scotland, I think it is. He formed this company called AMPS Electronics Limited, which I worked in and was associated with. One day he came to me and he said, got this idea that, I think he'd had the idea for some time, that I can make this circuit which is similar to a phase lock loop but works on amplitude rather than phase. And he goes on to sort of explain why, he went on to explain what advantages it would have. He was quite an inventor and had loads of patents, and he was probably better known for his work on magnetic recording, which he did before that, which I helped him a little bit on, but I didn't know much about magnetic recording, to be honest. So this talk is on the amplitude locked loop. So I'm just going to fire up these slides. So the amplitude locked loop and its application. So this is a servo system. Archie was a servo engineer. They also knew a lot about comms because he was a team leader that designed Europe's first Winchester hard disk. So you had to know about magnetic recording, communications as a communications channel in magnetic recording, digital recording, how to get the data off, use the phase lock loop, for example. And also we need to know about the design of the servo arm. So he knew a lot about servos and comms and stuff like that. Analog, he wasn't really into digital, that's to say, in the software side of things. Digital electronics, okay, but not the software side. So here's a signal, and just recall, there's AM, there's FM. We should know about that if we're engineers. If you don't, that's amplitude modulation, where we used to use it quite a lot. It's still used, but not quite so much in broadcast radio. But FM has been around since, for quite a long time, but in radio, since in the UK it was certainly around since late 60s, early 70s, and FM stereo in particular. And it's used because it's got a quietening effect. It's less prone to noise. A lot of people kind of wrongly think that because FM hasn't got any amplitude variations, therefore it's immune to noise, but it has other problems. It's not quite as simple as that. Whereas AM, of course, it's got amplitude variations. You think if you add noise to it, then it's obviously going to have problems with noise. But FM, people think it doesn't, but it does have problems nevertheless. So AM, mathematically, if you recall, is represented by this formula, 1 plus m cos omega modulation t. That's your message. In this case, just a single sine wave or cosine wave. And the carrier here, it has to be done on a carrier because otherwise everything will be mixed together. You've got to use carriers and you get all these different frequencies. In FM, there's no amplitude variations, but there is these phase variations, beta sine omega modulation t. Notice that the amplitude is 1, or considered to be 1. Of course, it's not exactly 1, but but that's normalized to 1. This thing here, M, is the modulation index for amplitude modulation, and that's got to be less than 1, otherwise you get overmodulation, distortion. You can just multiply cos times cos or sine times sine and have no DC term here, 1. But if you do that, you get what's called double sideband suppressed carrier. In other words, there's no carrier in there. Here, if you multiply this AM out, you get cos omega carrier plus m cos omega modulation cos omega carrier. And if you remove the DC, it means you just get a product of cos and a cos, and there's no term omega carrier. It's much harder to demodulate if you don't have the DC term in there. So that's what makes amplitude modulation, and not what's called double sideband suppressed carrier. Whereas FM, it's got this beta modulation index defined by the modulation frequency depth. That's how far the frequency sweeps from a center frequency, delta omega, divided by the modulation frequency. So in broadcast FM, delta omega is about 75 kilohertz. In radios, to demodulate AM, usually the so-called intermediate frequency, that was invented, I think, by Edwin Armstrong, this idea of heterodyning. That's 455 kilohertz usually, and at FM it's 10.7 megahertz is how it's used. I believe you get double conversions and all sorts of other things, but the basic idea is this. Beta, special sort of folklore, if you like, in FM, and that there's lots. If you look in the literature, you'll see lots of graphs with various values of beta and so on for things like thresholding in FM. FM is this property that it's got what's called the capture effect, which means if there's two FM stations close to one another, the higher of the two comes through, and the other one you don't hear. But when I say you don't hear it, you do actually hear noise, but you don't actually hear the station itself. Whereas in AM, you can have two on top of one another, and you just hear the other one in the background. You must have heard with cheap AM receivers with not very much selectivity, you could hear one radio station and then another one in the distance. But that doesn't happen in FM. FM uses more bandwidth. This delta omega is huge. AM's usually about 5 kilohertz to, depending on the country, maybe it's 10 kilohertz, high quality, wider bandwidth. Here it's 75 kilohertz. Because of that, Edwin Armstrong, who was the inventor, he had a lot of trouble really getting it sort of people interested. But eventually Motorola became interested, but I think there was a bit of a fight between him and Motorola, but that's for the history books. So here's the amplitude lock loop the way I draw it in my book, but the original, I'm just going to get the web page. This is the original patent that Archie took out in 1991, although we'd been working on this in the 80s, but I don't think he got the patent till then. So you can see over on the right here, the input, there's a linear multiplier, a modulus detector, this -1 and a +1, and an integrator for negative feedback, minus K upon S. It's a servo system. Basically what it is if you put AM into this thing, it strips the amplitude modulation. It doesn't have to be AM, but any kind of amplitude modulation. It strips the amplitude off of the carrier and leaves you with the pure carrier, recovers the carrier on its own. So you might think, well, so what? Well, there's not much point in that, but anyway, it does have its uses. The carrier, so it acts like a very high Q filter. It also produces this other signal, which is the reciprocal of the envelope. It doesn't produce the envelope, so it can't be used for demodulating FM, for example. But it is used. Well, I mean, but we did use similar sorts of applications. So here's my version of the amplitude lock loop. It's got a square law. We knew then we could either use a precision rectifier, had to be a precision rectifier, and not a normal rectifier, because normal rectifier's doesn't turn on till maybe 0.6, 0.7 volt or something. So we used an op amp in the early ones, but now you can use a square law, which also gives us a voltage which is proportional to the size of an AC carrier coming in here. The 2 is for scaling, so that when you have a set point here of 1, the carrier which comes out here is an amplitude of 1. So if you put 2 here, the carrier would have an amplitude of 2. And if you varied it, it would follow the variation. So you could generate AM, for example, if you just had a constant carrier going in here. But here I've got AM going in into this multiplier, a linear. It's got to be a linear multiplier. This is not an automatic gain control, although it does look a little bit like a automatic gain control. Automatic gain controls have got a huge dynamic range, maybe 120 dB or something. This has got a dynamic range of only about 20 dB, so it really needs a AGC before an amplitude lock loop to keep it in range. So how it works is if you were to put a pure carrier in there with no amplitude modulation, if M was 0, then you just get cos omega carrier here. If you square cos, you get cos squared into half plus 1 plus cos 2 omega carrier, so you get a term in twice the carrier. Ignoring the twice frequency for the moment, the DC term is a half, well actually multiplied by 2, so it becomes 1. 1 minus 1 is 0, and 0 in you get well, it's set up to have a 1 at the output. If you look at the original patent, actually, I actually put a 1 on the thing. Where is it? You see there's a +1 here. I haven't put it on, so it's maybe a bit harder to understand without that. Then if the amplitude varies, begins to change, if this carrier increases, you get a DC term increases on the square law. Set point is still 1, then this would be an integrator, let's say the filter. It doesn't have to be an integrator, let's say it's a filter, an integrator, and the integrator ramps and changes the output into the multiplier, which reduces the amplitude and keeps it constant. So if you put 1 plus M cos omega modulation T cos omega carry in, you get the reciprocal. This is the thing we initially didn't understand. You get the reciprocal of the amplitude. You don't get the actual envelope, you get the reciprocal of the envelope, but it does act like a high Q filter, and it gives you out the constant amplitude. So if you simulate it, originally I simulated this on a program, a software called Matrix X, which still to me was the best control system software. It's the first thing I ever simulated on it, actually. I was looking for something and Archie suggested to me, well, why not, let's try this. Matrix X kind of exists now. I don't think anybody uses it. National Instruments, I think, owns it now. But it's quite a long time ago, in the early 80s. But it was a fantastic package when we used it. I think it's better than Simulink or anything like that. So here's our AM input, 1 plus M cos omega modulation T cos omega carry T. So I'm simulating this just on MATLAB. Here's a recovered carrier. You can see slight waviness, so it's not perfect. So it's not fully recovered, the carrier, but so it's a tiny amount left. That's because the gain isn't high enough at that frequency. But it's good because it illustrates, how the loop works. It's not going to be a perfect carrier. If you go down in frequency, it's like an op-amp, then yes, you get more gain. So just like any control system, at the lower frequencies you get higher gain, and as you go up you eventually lose bandwidth. So it's a little bit of a tutorial explaining it all. I haven't really got time in this talk to explain it all, but that's what it does. Imagine it recovers a carrier without using what was generally called a hard limiter, which I'll talk about in a minute, and it gives you this signal which is the reciprocal of the amplitude modulation. To begin with, we couldn't think of what to do with that. We just thought it was a sort of artifact, we just throw it away, but Archie thought of a number of applications where you can invented this idea called inverse AM, where you modulate the inverse of the signal and then you use an ALL, an amplitude lock loop, which is short for ALL is short for that, an acronym. We used an ALL to demodulate it, but it didn't seem to be any use for that. Nobody was interested in inverse AM. There's standards to meet and so on. Who wants the inverse of the amplitude modulation? But it turned out later to have other uses that we didn't know about. Now, Archie was an expert in phase lock loops. He'd been the Signetics consultant or something for Europe or something. He got people ringing him up, he used to say, all over Europe, asking all questions on the phase lock loop chip that Signetics produced in the early 70s, which was, I was still at school at the time, so I didn't really know anything about phase-locked loops at that time. But he told me that there's a book, a Signetics book, which might still be around, with applications on the phase-locked loop, and every single one of them oscillated, of the applications, because it basically had a pure, well, equivalent of an integrator as a filter. If you have a VCO here, which is a normal phase-locked loop, it is an integrator, although it doesn't look like it. The equivalent transfer function of that is an integrator. If you put an integrator in here as the filter, you get two integrators, and the thing becomes an oscillator. So it oscillates in phase rather than sort of amplitude, but it is a oscillation you get out. So you need to stabilize it with a phase lead compensator, or just use a low pass filter, which is a cheap way of doing it, cheap and nasty, but not as good. So our FM goes in here. Our phase detector in this case is just a linear multiplier. There are other types of phase detectors, a whole pile of them, but that's the one that came on the chip that we used. So that's the one we stuck to, and we used that because it was equivalent, very similar to the amplitude lock loop. This is the free running frequency is set up to the incoming frequency here, which is the intermediate frequency of the radio, 10.7 megahertz. Although in the early days we used 455 kilohertz. The filter we used a lag lead compensator, and anyway that's sort of established work. The thing about phase lock loops and any kind of demodulator is that they're supposed to have flat amplitude, no variations in amplitude going into them. Not all radio receivers used phase lock loops. The posh ones did, and they used to advertise it, you know, PLL on the front or something. But they wouldn't sort of drift in frequency. But whichever method you used, it had to be no amplitude variation. So because of this, they stuck it through a hard limiter before it went in to the phase lock loop. Archie's idea was to put it through an amplitude lock loop, and he was sure you'd get better results. And we never fully tested that at the time because we had other things on our minds really to deal with. The phase lock loop's got a linear model like this, which is well known again, where the phase detector just becomes like a summing junction, subtracting. There's a transfer function which could be integrators plus phase lead, and the VCO is an integrator. And so in closed loop, because you've got an integrator in the feedback path, which is hardly ever you do, by the way, in a control system, but you do here, it behaves like a differentiator in closed loop. And it was supposed to, I think at the time, it was supposed to give you 3 dB extra lower noise levels or something with a phase lock loop, rather than, apart from its other nice properties, as opposed to other methods. The traditional method of demodulating FM was to differentiate it with some kind of high-pass filter, and that converts it into amplitude modulation, and then you envelope detect it. But there are other methods like quadrature detectors and things which are much better nowadays, and eventually we went on to that. But the point was to keep the amplitude constant as it's going in, whatever method you're using. So to keep the amplitude constant, which traditionally used and may still be being used in some areas, is it's a limiter, which is usually just a chip. You can make your own, and it just is followed by a bandpass filter, because what you get out of here is a square wave, and you just need to take the fundamental out to convert it back to a pure sine wave. So if you look at the basic idea, here's a sine wave going in, and it triggers high at the zero crossing and back down again. So it produces like pulse width modulation, which you then filter. You can filter the DC out as well with a bandpass filter. And people think, oh, that's fantastic. It just gets rid of any amplitude variation, gets rid of it, and everything's fine. Except it doesn't. What happens is that additive noise gives uncertainty in the zero crossings, and so you get jitter here in the at this point in time, and that introduces noise. So you've converted your amplitude variations into phase variations, and it's kind of common sense because there's no filtering action in this. It's just a threshold, a nonlinear kind of threshold. There's no filtering in it at all. And I actually realised that, and a lot of people have. We talked to engineers at various places at the time in the UK, and I remember talking to them at the BBC, and they were saying things like, when you've got a lot of noise, it's better to take the limiter out altogether. It's okay at high signal to noise ratios, but then you get rid of the limiter. And we thought this would be a replacement, and we went ahead and made a hybrid type circuit out of it, which I was involved in at the time. You can read more about the theory of the amplitude lock loop in this book, which I wrote a few years back, called Feedback by Springer. If you do buy it, or the e-version, any proceeds from me goes to charity, you'd be pleased to know. So it's not like I'm profiteering out of it. Okay, I think it's quite a good book myself, even though I say so myself. So let's go and simulate the amplitude lock loop and see what happens. So I'm going to compare it with a limiter on a phase lock loop. So this is a community edition of LabView, by the way, so anybody can download this. It's really, I recommend you do if you're into LabView. It doesn't cost you anything. So this is quite a big simulation. I had to do just about everything myself. Wasn't that many there's a few library functions at the time, but like basic filters, but there wasn't an awful lot. So I generate FM here with a frequency of 10.7 megahertz. It's got a huge sampling rate. I mean, it would have been possible to scale it all down, I know, but I wanted everything to be kind of as genuine as possible. So the early PCs probably wouldn't have been able to handle this anyway. So it wasn't until later that, I don't know, about 2004 or 5 that I had something like this, and maybe a bit later after that. Also simulated a phase lock loop over here, and beat the National Instruments to it because they didn't have a phase lock loop. I was always interested in simulating phase lock loops. Notice it's set up to 10.7 megahertz as well. That's the free running frequency. This frequency here, that's just the carrier frequency there, by the way. The amplitude lock loop is here. Doesn't look like much here, and this is a hard limiter, and I can switch between the hard limiter here, and the amplitude lock loop with that conditional function. This is the filter after the limiter, and it doesn't, the ALL amplitude lock loop doesn't use that filter. It just goes straight into the phase lock loop over here, and then this bit's for the spectrum. So let's have a look. I'm going to put a small amount of noise. You can't put sort of zero noise, but a small amount of white noise, additive noise. Here's our demodulated signal, and I can vary that. So it's quite a nice simulation. So that's a phase lock loop demodulating the signal. I'll set it to about 2 kilohertz. Amplitude lock loop output is at 1 because the set point is at 1, so it should be about 1. This graph is also the amplitude lock loop output. When I flick the switch, it changes to a hard limiter, and so it's slightly different looking output because it's going through the bandpass filter. So let's look at the carrier here, and this is because it's FM. You can see that I'm keeping the frequency deviation at 75 kilohertz, so this bandwidth here doesn't change. Centered on 10.7 megahertz. I'm going to average the noise at the floor noise, sorry, on this. A beautiful LabView spectrum analyzer. That's showing that over here, mine is 85 dB. So I'll store that, clear it. Then I'll put the limiter on, and I'm going to average that. So the limiter is showing minus 66 dB, which is a lot worse That's higher up because it's negative, it's dB. So it's a difference of almost 20 dB there, even at that signal to noise ratio. So you can see the improvement of using an amplitude lock loop. Obviously I can change this. Let's move it up to 0.1 and it should be a much, let's go ahead again. So this is the limiter output. Let's store it. Oh, I don't know if I stored it there. Store it. And then this is the amplitude lock loop. So the difference isn't as much now. So there's still a 5 dB difference, you can see. And eventually if you increase it even more, you'll find that the difference is smaller and smaller, and then it becomes there's hardly any difference. So the amplitude lock loop does give a difference, lowering the noise floor. But what does it do to the actual demodulated signal itself? Well, let's have a look. It's the same program, but it's better to write two programs because otherwise you're fiddling around changing it to baseband frequencies. I've set it up again to 2 kilohertz. It's near enough. That's 0.01. It's where we started the last time. This is no limiter on. This is the amplitude lock loop rather. And store that. And then put the limiter on. And you can see the noise floor is increasing. So that I'm using the same, sorry, I'm using this, should be, it's a difference there of about 74 to 80 or 10 dB. That's actually quite a, scale is a bit on the big side. Move that down. Okay. And you'll find a similar thing when you increase the standard deviation of the noise. It's still a little bit better with that's with the limiter. So let's have a look at that. I'm going to average that. Store that. Now, amplitude lock loop. It's down here. So the noise floor is 69 to 77. So that's what's that? 8 dB down the noise floor. It's higher frequencies and. So the basic operation did work. Archie was right. Seems the noise floor did go down, which we didn't check it at the time because, as I say, we were working on things like co-channel interference. It seems a bit silly that we didn't do something as obvious as this, but we didn't have all the equipment necessary, and I didn't have fancy simulation tools available. Matrix X couldn't do spectra and things. It could do a lot of control functions, but I couldn't do these kind of things. So this gives you an idea of the power of LabView and a little bit of history on the phase lock loop. I'm going to give another video on the phase lock loop, but and the amplitude lock loop. It'll be coming up. So in the meantime, thank you very much.